All right, welcome back, everyone. So we already saw that we can qualitatively describe a potential relationship. So, for example, if we have um, our x variable and y variable, and we've already got our scatter plot, we can see that there seems to be some slight trend. And so far, all of this has been qualitative. Now we want to go ahead and actually make this more quantitative. So when we claim, so in other words, our first step was to describe the relationship, a potential relationship. Um, Qualitatively, we went ahead and we said that we can, for example, describe the trend that we observe, whether it's linear or nonlinear, and then we can describe the strength and direction. So the strength really only makes sense generally, like if it's linear or nonlinear, we can always describe strength. But if the trend is linear, then we can also describe the direction, whether it is a positive direction or a negative direction. Now, what we're going to do is we're going to go ahead and actually quantify these general statements. So these are not precise at all. It's just we're saying we believe that this is true based on a visual. Now we want to go ahead and actually back up the statement with some numbers. So the next thing that you're going to do once you believe that there's a linear relationship between the data, you're going to quantify this relationship between the x and the y variable, whatever they may be, by finding the correlation coefficient. Now, the correlation coefficient is actually called the sample correlation coefficient because it is the value that's computed from the sample. And the reason for that is that we're basically taking the sample mean and the standard deviation for the x variable and the y variable. And we're essentially creating the z-scores. So we're standardizing no matter what the values are or units are for x and y, we're going to go ahead and create our standardized number line. So here you can already see that it's standardized. So the units are no longer, whatever they may be. So here we have our center. Here is x bar. And then here is y bar. And you can go ahead and see that there is this trend if you make a horizontal line and a vertical line at the averages for the x and the averages for the y. So here above, you can see the distribution of the x variable. It's a histogram. On the side, we see the distribution of the y variable. And what you observe is that separately, if you only look at the histograms, if you only look at these, they kind of look the same, but we can't really determine whether there is a relationship or not. So we have to plot their corresponding z-scores. So here we can see that this point has a z-score that's around 2.5. And notice that the z-score on the y is fairly high as well. It's pretty close to 3. And so what that means is that there's this positive trend that high z-scores in the x variable tend to be associated with. So for example, here's another one. Here's a high, in other words, above 0 data point. And then that also corresponds to a positive z-score in the y variable. And so we can see that there is this trend that positive z-scores in the x variable tend to be associated with positive z-scores in the y variable. So that's a positive association. They move together. Now, take a look at something, for example, here. This data point has a low z-score in the x, and it also has a low z-score in the y. And so do all of these other points in here. Maybe let me make it a different color so we can see that better. Let's make it pink. So these are the data points that I'm talking about. All of these are to the left of the mean in the x variable. And their y variable is also below the mean. So again, low in the x, low in the y. So again, that's also a positive relationship because they are the same. So all of these data points that we see here in this quadrant, basically, and in this quadrant contribute a positive product. So if you take the z-score in the x and you multiply with the z-score in the y, if these have the same sign, you're going to get a positive times a positive, or you're going to get a negative times a negative. In either case, they're going to produce a positive value. So if you generally have data that is in this region and in this region, kind of like what we've got here, then we're going to obtain what is known as a positive correlation coefficient. On the other hand, if you have data points that are here, in other words, take a look at this, they are below average in the x. So you can look at them up here, like that's the data point. But that data point also has a y value, and in the y value, it's above average. So it's over here. It's above the center. So that's not good because we basically have the z-score in the x being negative, but the z-score for the corresponding y variable is positive. So when you multiply them, you're going to get a positive times a negative, and that is going to produce a negative. So here is what you observe. All of these points in this quadrant and all of the points in this quadrant will produce negative products. And so if you go ahead and for every data point, take the product of the x and the y z-score and add those up, you're going to obtain a value that is either positive or negative. And then depending on the general trend of the data set, you will get a value that is positive or a value that is negative. Now, there's actually more to this. Not only is it just going to be positive or negative. So let me go ahead and draw those lines. So this is where the center would be. And you can see that a positive correlation, positive trend, has more data points in the quadrants that result in that positive product. So again, when you do the z-score for the x variable, multiplying with the z-score for the y, you can see that all of the data here is positive. There are these points that would result in negatives, but there's more positives than negatives. So your correlation coefficient will be positive. So that's the first thing that we want to know. The correlation coefficient being positive tells you, so if the correlation coefficient R is positive, then that tells you that you have a positive correlation. And if you go ahead, so let's go ahead and do that quadrant stuff again. So we can observe here that we have more data points in the negative regions where we would get that product being negative. So there's negative and there is negative. And here again, you get 1 or 2 points that would be in the positive, but overall the general trend is negative. And here you have perfect cancellation. There's around the same number of points that would be in the positive and in the negative. So the net correlation coefficient is 0. All right, so that's one of the main things that we want to note. So if R is around 0, then that means that there is no correlation. There's no positive direction or negative direction that is highly apparent. And if R is less than 0, then that results in a negative correlation. All right, so let's just note that now we're quantifying. We're using values to describe the direction. So we can check this off. All right, now there's also one more thing to note. Because the correlation coefficient is based on the product of z-scores, there's this standardization, it can be shown that the R value can only be between -1 and +1. So you can prove that mathematically. So the largest that an R value could be is exactly 1. And if you get a correlation value that's exactly 1, it's positive. And 2, you got to have perfect correlation. So that means that basically your data lies on a perfect straight line. So if R is equal to 1, we're going to go ahead and say that that is good for us because that means that our trend is actually linear. It's really important that R actually is built around this idea of linear association or correlation, but it can still be computed from any data set. So this formula you can apply for really any data set. And we're not going to do it by hand. We're going to use StatCrunch. But let's go ahead and make a note of that. If R is 1, then that's perfect positive correlation. And if you go ahead and remember that for R equal to 0, that means there's no correlation, then you now have this way to quantify the strength of the linear correlation. The closer you are to 1, the stronger the correlation is. The closer you are to 0, the weaker the correlation is. Now, similarly, on the opposite side, if your correlation value is -1, so -1, it can be shown that -1 is the smallest value that's possible for the correlation coefficient. And if the closer you are to -1, then the stronger the pattern is. So in other words, the closer you are to 1 or -1, the stronger the correlation is. So you basically ignore the sign. And we're going to go ahead and say, if you take the absolute value of R, and that's very close to 1, then that means they have a very strong correlation. And it should be very apparent from your graphic, by the way, from your scatter plot. It should be, if you show it to anyone, they're going to say, oh, yeah, I can definitely see that there is a pattern in that data. So whether it's going downward or upward, if it's exactly lining on a straight line, most people would agree that that's very obvious, and a very obvious relationship. But as the data points drift away from one another, the correlation coefficient will drop. And again, the closer that the correlation coefficient R is to 0, the closer that is, then the weaker the correlation. So we can go ahead and check off the strength as well. So only go ahead and compute the linear correlation coefficient if you have already observed the relationship and described it qualitatively, because now you want to go ahead and say, justify the fact that, hey, there is in fact this, the trend that I observed in my scatter diagram is in fact positive or negative, and it is in fact strong or weak. And so the last thing I want to say is that the R value is, in other words, a way to standardize. So R is always, always, always going to have these in this meaning. If R is positive, a positive value, then you have positive correlation. If R is negative, then we have a negative correlation. And the closer that we are to 1 or -1, then the stronger the pattern that I observe. The closer R is to 0, the weaker the pattern that I observe. So let's go ahead and actually practice this. Here in this example, we have no actual data, but all we have is scatter diagrams. So we can go ahead and say, okay, we did step 1, we have scatter diagrams, and then we have potential correlation coefficient values. And they are listed here on the top. And what I want you to do is I want you to go ahead and match these. So without doing any computation, go ahead and try to apply the rules that we just did and try to match them. So for example, for A, I can tell that there seems to be a negative trend, and it's not a very good trend. So I am going to go ahead and take a look at the negative values. These are the potential correlation coefficients for A. And right off the bat, I'm going to go ahead and say that it cannot be -1, because that would be perfect linear negative correlation, which would land on a straight line like this, which I do not have. And this trend is actually not quite strong. You can see that my oval, if I were trying to draw an oval, it would be a pretty large oval. So I don't want to be close to -1. I want to be closer to 0. So there's really only 2 values that are possible. I wouldn't pick -0.85. Part of the reason is there's another value right here, F, that also has a negative correlation, right? Negative pattern, but the data points are closer together. There's a tighter or a stronger pattern in this data versus the pattern that I observe in A. So again, if you draw an oval, this would be a very thin oval. If we draw an oval in A, then that would be a wider oval. So that means that the pattern isn't as strong. So F is stronger, which means that I need to be closer to -1. So the most appropriate value for R for F is negative 0.85. And the best or the only response really for A is therefore a correlation coefficient of negative 0.5. All right, I'm going to go ahead and leave it here and wait for you to tell me what is the correlation coefficient for some of the remaining plots. Thank you. I'll see you in the next video.